Good afternoon, everybody. Thank you for the organizers for inviting us to show you the status of the statistical model, in particular for lower energy, although I will be saying a few things about LHC and RIC, of course. So I will talk about strangeness and charm in the statistical model. This is based essentially on our review in Nature with Johanna, Peter, and Krzysztof, with whom essentially all of this work is done. And I will make an introduction to the statistical model, although this is an expert audience, we don't really need to discuss this in extenso. This is the compilation of up-down strange hadrons, some of them, not all of them, but some of them, the most abundant, pions, kaons, protons, and lambda hyperons. And you see that at lower energy, the energies, AGS, SPS, RIC beam energy scan, of course, the chemistry is very different compared to the higher energies. And in particular, at the higher energies, the mass ordering is so obvious, and then it's natural to think of the statistical model application to describe these yields. And what is this statistical model, or the thermal model, or the hadron resonance model? It's in a way maybe the simplest model. Is a snapshot, gives a snapshot of the collision at the chemical freeze-out, and in a way is the earliest in the collision timeline that we can look with direct hadronic observables. And via comparison of data to this model, we test the hypothesis of hadron abundances in chemical equilibrium. Of course, this is the picture, the conceptual physical picture is simple. The devil is in details, as in many models, of course. One needs a complete hadron spectrum. This is what PDG provides. The question is whether there are extra states, which we have just discussed concerning charm states during the talk of Min-Hei. We need canonical approach at low energies or in smaller systems. We need to understand the data well, for instance, to control the fractions of weak decays. So yeah, these are the caveats or the details one needs to watch. And then the formulation is known. Grand canonical partition function is written here. And you see the degeneracy factors, the energy momentum relation, and then the presence of the chemical potentials. For baryon, isospin or charge, strangeness and charm. And those ensure the conservation on average of quantum numbers. And there are a few initial conditions that help fixing some of these these chemical potentials up to one of them, namely the baryochemical potential, which remains a fit parameter. So three initial conditions: the relation between isospin and baryons, and the neutrality in strangeness and charm, fix I3, a mu charge or mu I3, a mu S and mu C, and then only mu B remains, as I said, as a fitting parameter together with the temperature. About the hadron spectrum, this embodies the low energy QCD, of course. We use vacuum masses all the time, this is something that can be discussed, but this is sort of the default. The hadron spectrum is well known up to about 2 GeV in mass. You see here the abundances, actually is the cumulative distribution of mesons and baryons as a function of mass. And you see that beyond 2 GeV, the spectrum is presumably, one can infer from this plot that the spectrum is less well known. This form of this hadron spectrum is leading to the so-called Hagedorn temperature, namely the temperature where the density, the energy would diverge in the for point-like hadronic gas. Then hadrons are subject to strong and electromagnetic decays, of course, the resonances. And you see here the fraction from weak decays, also from feed down from higher mass resonances for several species. The typical ones, pions, kaons, protons, lambdas, and psi. And you see that this a dominant component is in many cases of this hadron, certainly for pions and for protons and also for lambdas, are the contributions from feed down from higher mass resonances. This is, of course, a temperature dependent quantity, clearly. We do in our treatment consider the widths of resonances. Bright-Wigner widths are being used, and this is important mainly at lower energies, in fact. So it is a detailed thing, but is in our model. Here you see a dependence on the temperature of the hadron densities. For point-like particles is the dashed line. You see here the Hagedorn divergence, more or less. And if one would consider finite size objects, then this divergence is tamed, so to say. But you see that at the temperatures of the order of 150 MeV, we are dealing with a rather dense system, certainly. It is, I mean, this divergence, this in density is sort of unphysical, one would say. Traditionally, this was finite size, also spherical hadrons were being used in our own treatment, as in many others, with a rather moderate radius parameter of 0.3 Fermi. Nowadays, we don't use this anymore because we have considered another way of treat the interactions in the dense system, and I will say a few words about this in a minute. Canonical correction, as I was saying, is important for lower energies, and this is needed whenever the abundance of certain hadrons, for instance, strange hadrons, or also charm hadrons, in particular, maybe charm hadrons, because those are even rarer, well, needs to be enforced via exact quantum number conservation, and this is done via the so-called canonical correction. And this is was demonstrated, in fact, that one can do the canonical or calculate the respective canonical density from the grand canonical calculation, employing a ratio of Bessel function, where the argument is the total number, not the density, but the numbers, the abundances, densities times volumes of particles with a given quantum number. Strangeness is being here illustrated. So for kaons and lambdas, for instance, one would have the ratio of I1 to I0. For psi, one would have I2 over I0, and so on. For phi, since there is no net strangeness in the phi, the canonical density is equal to the grand canonical one. You see here the suppression factor due to the canonical treatment for this rather largish canonical volume of 1,000 Fermi cube used in this plot. This was our default up until now. In this business, one often talks about a strangeness suppression factor, gamma S, a non-thermal fit parameter, which was sometimes used. We actually don't use it for central collisions. There is still some debate whether it is needed. Sometimes it's employed, as I said, and it comes out in the region 0.6 to 0.8 at lower energies. I think in general, most of the people, I think, in our community would agree that at least for central collisions, it is not needed, even at lower energies. All right, so the thermal fit essentially employs, as I said, the available hadron mass spectrum in our code. I think meanwhile, we have updated it. We have almost 600 species. I should maybe update this 555 species to about 600. So we minimize the chi-square between data and model, where the sigmas here are the experimental uncertainty, statistical and systematic, of course, and then the fitting parameters are temperature, biochemical potential, and the volume when we fit yields, which is our default. Sometimes fitting ratios is employed, and then the volume, of course, drops out. This is how successful the model is at the LHC. And this plot was shown before in the meeting. You see that over many orders of magnitude, 9 orders of magnitude, the model describes the data very well, particles and antiparticles. And the resulting fitting fit parameters, temperature, biochemical potential, and volume are being displayed here. And you see that temperature comes out to be very close to the phase boundary, or at the phase boundary as predicted by lattice QCD, 156 MeV about, and the biochemical potential comes out to be practically 0, as you see from the abundances, the quasi-identical abundances of matter and antimatter in this plot. Also loose bound objects. Oops, I did an escape. I don't know whether you have lost my window or not.
No, we still see it.
We see it. Okay, very good. Right. So also loose bound objects like the deuteron, the hypertriton are being described. There is quite some discussion. Why is it so? But I will leave that aside for now. So in this plot, which shows the same information, but as a function of mass, I show the specifically for the LHC case, the contribution of the case of resonances. You see that the data points, which are the red points and the green squares, are fitted very well by the blue lines of the model. So it's the same information transposed in another plot. But the primordial densities, which are this dashed line, are of course very different ones. I mean, factor of almost 4 for pions, and factors of 2 or so for kaons, and large factors also for protons and lambdas, as you see here. But for particles that are essentially free from decays, like the omega, hyperon, the deuterons, the helium-3s, and hypertriton and helium-4, we can do a fit separately, and we end up with a temperature which is essentially the same, like the fit of the global set of particles. So that sort of demonstrates that we are not sensitive anymore to the presence or to the absence of possible higher mass resonances. Right, so the interactions which were traditionally modeled or mimicked via eigenvolumes through this radius parameters of 0.3 Fermi is something that is debatable. We have tried ourselves several cases. Many people spent efforts in playing with this. In fact, none of these investigations, as interesting as they are, of course, is fully convincing, I must say. I mean, without wanting to be too sharp, but this is essentially how we see it. The right way to do interaction is what we think is the way we have achieved it recently in a collaboration with Pokman Law, namely treating interactions in a S-matrix formalism, employing the pion-nucleon scattering phase shifts. That includes also non-resonant contributions. And this treatment actually solved the so-called proton puzzle, namely the fact that too many protons were seen in the statistical model. So what this treatment leads to is a reduction in the proton density in the model by about 17% or so. We have done this in the non-strange baryon sector. The strange baryon sector is still missing, but we have estimated that the corrections are of the second order. So this is not anymore so relevant as the non-strange baryon sector was before. Right, so this is then the outcome of the thermal fits. As you know, a strongly increasing temperature parameter and the saturation for higher energies, and a strongly decreasing baryochemical potential as a function of the collision energy. This limiting temperatures here is per se a remarkable observation, and this hints to the fact that a physical limiting temperature is being reached, different than, nota bene, different than the Hagedorn divergence temperature. This is essentially the phase boundary temperature. We know now, also employing what we know from lattice. And this is the first time hadrons come to being from a deconfined state. What happens at lower energies here in the region of increasing temperature or decreasing towards lower energies is subject to discussion and subject of this meeting, and per se something very interesting. Right. Here is the grand view. Now we take from this individual fits that these points are at different energies of rather different sets of hadrons, but never mind, you see that there is a consistent smooth picture. So we take parameterizations of those fits, and these are the black lines for T and mu B, and look how individual ratios are being described by the model. You see in the upper panel, pion to proton to pion and antiproton to pion, as well as neutron to proton, very well described by the model. And we see in the lower panel the famous horns, namely in the K to pi plus and the K to pi minus, no horn in the lambda to pi, or a more pronounced, more sharp horn. And these things are related, as I was commenting, I think in the first day, through the strangeness conservation and the associated production of K and lambda mesons. So what the primordial, so to say, the peak here in lambda to pi is the defining one, so to say, because it's in the lambda to pi that the competition between an increasing temperature and a decreasing baryochemical potential leads to this peak. And the K to pi, K plus to pi plus, is a derived through strangeness conservation quantity in a sense, or a resulting quantity, so to say. Right. Up until now, we used a constant canonical strangeness conservation canonical volume of a rather largish value, as I was saying. So we have now quite good indications that this quantity shall be multiplicity dependent. There was a recent study by Jean Clemens, Pokwan Lo, Krzysztof Redlich, and Natasha Sharma on proton-proton and proton-lead collisions at the LHC, and they have demonstrated that a data description is being achieved with this multiplicity-dependent canonical volume. Now we employ this idea and do this as a function of the energy. Here is the particle multiplicity, the charge particle multiplicity, then rapidity density as a function of the collision energy. You see roughly two regimes of a steeper and less steep increase of the particle multiplicity as a function of energy. We parameterize this. And if we now employ a canonical volume dependent on particle multiplicity, not so much changes actually in these ratios of kaon to pion and lambda to pion. On the right side here, I show the ratio phi to kaons and psi to phi and omega to phi. Of course, psi to phi is a very sensitive quantity because the canonical suppression enters in the second order for the psi and doesn't enter for phi. You see here that the available data, including the recent one from STAR on recently measured at 3 GeV, which you have seen in a presentation by Frank yesterday, is not so well described with this parameterization of the canonical volume with the existing temperatures. If we we make the decrease of the temperature towards lower energy a tick less steep, namely that values will be at lower energies about 10% higher, then with a different parameterization of the canonical volume, we achieve a better description of these ratios in the right side here. So it seems that the current data would favor a slightly less steeper decrease of the temperature. We have not updated the value. This is just a preview, a hint that things may change a bit, but this will be in details. This is how it looks on the phase diagram, how the chemical equilibrium points look at on the phase diagram T and mu B. You have seen some of these points in previous presentations in this workshop, and you see this very steep decrease of the temperature at very high baryochemical potential, which I was just commenting, maybe a bit less steep, but essentially at the border, at the upper border of our current uncertainties, not much above. Yes. Now you see here different sets of points from different codes, different people who did it, and this leads us to conclude that model or code uncertainties are quite small. So this is quite a nice agreement between the different groups doing more or less the same thing. So on the light quark sector, we have seen that the data imply that the hadrons are produced at chemical equilibrium. And what we have employed is what we call a minimal model. It's our own bias towards a minimal model, namely a minimal set of parameters, as few as possible. And these are the three: temperature, baryochemical potential, and volume. And with this,
5 minutes left.
Access, 5 minutes, thank you. Right, I understood it correctly. So we have seen that this approach provides us a way to access the phase boundary. And now we try to gain more insights from heavier quarks. And heavier quarks are, as you know, produced in PQCD hard processes. And what it implies for our model is that we throw in a certain amount of CC bar pairs. In this example here, about 10 at the LHC, leading to a charm fugacity of the order of 30. And this fugacity you can see manifested here for the J-psi meson, which is enhanced compared to the thermal production by about a factor of 8,000, namely GC 30 to power of 2. It has a C and a C bar quark, right? So what is assumed in this approach is that there is full thermalization of C and C bar quarks, namely they move freely within this volume of about 4,000 Fermi cube. And we assume full color screening in the Matsui-Zatz picture. And these assumptions were put forward essentially at the time when the model was proposed by Peter and Johanna in year 2000. The model has large predictive power, and we have applied it for several hadrons. And here I sketch very briefly how this is done. So we do thermal model calculation in the ground canonical ensemble. We have T and mu B fixed from the UDS sector, the volume as well. We employ a canonical treatment because of the rare production of the charm quarks, and we derive the fugacity factor from this balance equation where the number of available C and C bar pairs are thrown in the system, as I was saying. Of course, we need them, and we have to employ either experimental or PQCD production cross-section. We need shadowing for lead, and so on, right? Okay, so when we apply this in mid-2000, the RIC data were available and were being described reasonably well, quite well. And the LHC data were still at the horizon, and we endeavored this prediction that the nuclear modification factor for the J-psi would be significantly higher at the LHC because of the larger charm production cross-section, and this square factor, GC square, will then predominate, and this will lead to this. And this was essentially confirmed, very well confirmed by the data. You see here at mid rapidity in the upper panel and the forward rapidity in the lower panel. So essentially the model is sort of vindicated by the data. As I was saying, we can predict all the variety of charmed hadrons, mesons, and baryons. You see here the full zoo, including a C deuteron, a C triton, a pentaquark, the triple charm omega hyperon here. Very rare rates, but this is something that we hope to measure in the future at the LHC. We predict transverse momentum spectra to, here is the ratio of lambda C to D meson, the ALICE preliminary data, and our own prediction, which fits reasonably well the data. There is discussion whether the charm spectrum is complete. I leave that for the questions. And I would like now to address charm at lower energies in the last few minutes. And the question is if charm thermalizes at lower energies or thermalizes fully as we assume in our model. And this if, as I have written it here, is of course a big if. The model itself is conceptually easy to be extended, of course, to lower energies, was in fact even proposed starting at in relation to the available data at the SPS at that time in 2000. Actually, the litmus test for the model also at lower energies as well as the higher energies is the relative production of psi to S to J psi. This is in the thermal model around 4%. And is in proton-proton collisions around 15%, as you see here in this plot. This is that the only available data point is at the SPS measured by the Na50 collaboration. So, of course, we shouldn't have other indications, namely V2 and nuclear modification factors, also jet charm quenching in the QGP. But within the model itself, this simple ratio, psi to S to J psi, is a very strong test. Of course, this is simple in the model. In the experiment, it's a very difficult measurement given the low abundance of psi to S and the smaller branching ratio in E plus E minus or mu plus mu minus. It will be measured at the LHC, but not, well, we do have a preliminary value and it will be published, but with a precision measurement is a goal for round 3 and 4. Now, at lower energies, at the SPS and RIC, in fact, the decrease trend as a function of centrality is rather similar. There are in details, this decrease shown here in the ratio of J psi to the CC bar yield. This trend is similar, as I was saying, at lower energies and different at the LHC. The data at the SPS are described by the model in what concerns the trend. Now, the uncertainties, of course, of the model are large, given our rather poor knowledge of the charm production cross-section. So constraining the model at lower energies, at the SPS energy, implies or needs a very good measurement of sigma CC bar. We have the full chemistry as a function of the collision energy as well. You have seen a version of this results in the plot in the talk by Chin, you see it here in terms of yields as a function of energy. You see that the chemistry is very different at lower energies compared to higher energies, simply because of the high mu B. The baryons are enhanced relative to mesons at lower energy compared to the higher energies. There are some non-monotonic ratios. I show here one, the J psi to D meson shows a minimum at intermediate energies between SPS and RIC. And maybe the RIC data at the intermediate energies, the Phoenix data and STAR data are being prepared for publications. They are preliminary for the moment. Maybe they could tell us whether this minimum is being realized or not. Right, this brings me to the conclusion. In the statistical hadronization model, the hadronization is a rapid process, order Fermi over C or so, in which all quark flavors take part concurrently. There are variations to this, but in our model, we consider that that all happens at the same moment. Then charmonium and open charm states are generated exclusively at hadronization, at chemical freeze-out. As I was saying this, we assume full color screening. And you see that the model is reasonably or very successful in reproducing the J psi and open charm data at the LHC and also at lower energies. And importantly, this gives us a handle for the hadronization temperature with a mass scale, that of charm quark, which is very different, well above the temperature. This is not the case for the strange quark, right, which is has a mass of the order of the temperature of the hadronization or phase boundary temperature. Of course, we know there is competition, and the authors are in the audience. The kinetic model is also a successful treatment, and it assumes a continuous destruction and regeneration of D mesons and J psi mesons in the QGP. We all agree that at the LHC, the limit of quasi-full production at the phase boundary, quasi, I am saying, up to about two-thirds or so, is being reached, at least for central collisions. And we think that discriminating the two pictures, the dynamical one and the the production at chemical freeze-out at the phase boundary, would provide us another fundamental answer to the question related to the fate of hadrons in the confined medium. But for this, at least at the higher energies, we also would need a very good measurement of the charm production cross-section. That is in sight, but it will take a bit of time to have it at the level of plus minus 10%. And once again, this, in order to test the model at lower energies, this ingredient is also needed with a similar precision, which is a challenge for all of us. Thank you for your attention.
Space for some questions, Ralph?
I do not hear.
So good afternoon, Anton. Took a while to get the microphone going, sorry.
Yes, this is good, yes, thank you.
So thank you very much for this very informative talk. There were some things I didn't know, so I learned quite a bit here. And I also very much like your concluding statement about the fundamental question of the fate of hadrons. I fully agree with that. So that's all great. I had a question on the rig situation, I think 3 slides back. Yeah, no, next, forward, just 3 slides, 30 or so. Since you did write out the cross sections there, I was wondering how that relates to what Xindong today reported for the d sigma dy, which was like 130 or so, which is actually not that far from the 120 value of Phoenix.
Right.
And you're using 63 here. Is that potentially something to worry about?
Yes. Yes, I think it is. We knew since some time that our description of the rig data is best with rather lowish charm cross section. Yes, I think this is it's fair to admit. At the time when we actually did it, the situation in the data was less clear than it appears now. Of course, there is some shadowing of charm at RIC as well, and this is the effective cross section. So after the shadowing. So yes, this may need to be reevaluated. I would agree. And it may be that the model would overestimate a bit the data. It could
remember at the time when we did this, there were 2 results for the charm cross section that differed by a factor of 2.
Right. Right.
Okay.
Right. So yes, I think this is it's good to admit. It's a good comment. Thank you. Yes, we will be looking into this at some point. Yeah.
Okay, there is another question by Enrico.
Hello, Anton. I was interested by your slide 32, where you show the various ratios and in particular the J psi over D0. So as you know, one possibility now is to try studying the J psi below top SPS energy. And it seems to me, let's say this ratio varies, this is a logarithmic plot, so it varies quite a lot in this, let's say, SPS region. So since the ratio J psi over D or J psi over open charm was suggested as a way to quantify the anomalous suppression, then is let's say this plot would tell me that this is not so, let's say, so immediate, because this quantity can vary a lot, so that if I compare to different energies, this ratio, then I might get, for example, an enhancement of the J psi with respect to the D0 going towards low square root of S, and this is nothing to do with, let's say, potential dissociation effects or anomalous suppressions or like that, or this is part of the game here.
You see, what is assumed here is, once again, we have full color screening, so no J psi preformed prior to chemical freeze out to the phase boundary. And yes, this is what we predict, and it comes, I mean, it's easy to understand the physics of it is simply the canonical suppression towards lower energies. Because of the charm cross-section dives, the canonical suppression is so strong that the CC bar is favored, so to say, right, compared to the open charm. Yes, yes.
Can I follow up on that? Because I'm not sure if I understood it. I thought, I mean, is the increase of the J psi over D0 related basically to also the increase of the lambda C? Because now you have basically lambda C plus anti-D production instead of DD bar.
It's not related. No, the lambda C increase is driven by the baryochemical potential.
Yeah, but you basically and conservation means that you have basically the anti-D with associated with the lambda C to conserve charm. So you don't need the D0 anymore.
Yes, of course, the charm conservation is there, absolutely, but it is, J psi is decoupled from this. The charm conservation takes part in the lambda C plus D sector. The J psi is detached from this because it is zero net charm, right?
It's not canonically suppressed.
Yeah, this is exactly what leads to the increase.
Yes.
It's right plot here. Yes.
Okay. There is also a question from outside. Frank?
Yeah, Anton, a very nice talk. You did mention, but I didn't quite get it completely, the hydrogen, the hyper hydrogen 4 that was off by about an order of magnitude. You mentioned that actually in a new iteration, you had more agreement, or can you briefly remind me again what you just said there?
You were referring to, well, to my comments about this plot of the yields at the LHC.
Yeah, well, I was more talking about the measurement that started at 3 GeV.
Ah, wait a second. Yes. Here, right. So I do not show here hypertriton. What I show from star is the psi and the phi yields, and this is the point here. So phi to k is this point from star, and the psi to phi is this blue dot here. I was meaning those only, and they are better described together, so to say, by, as I was saying, a bit less steep decrease of temperature towards lower energy, I think. That was the comment. Of course, if we would update this, it will imply a bit of change in the hypertriton and in hyperhydrogen 4 as well, right? Which is, we don't describe right now. The star measurement is indeed definitely higher. A preliminary measurement of star is definitely in the hydrogen 4 lambda is definitely
an order of magnitude higher. Yeah. Okay. All right. Okay.
This will not change much. I mean, this update is rather little, and it will not change much our prediction of the in the hypernuclei sector. A bit.
Okay. So let's take the last question.
So Anton, Tatiana is here. I still have a little bit of problem with this transition temperature, or maybe better to ask the question in the way transition between what to what. And let me say, because well, we know that at 150 MeV chiral condensate is depleted only by 50%. And we also know that at 150 MeV, raw meson still has a bump structure. So I do not really know transition from which meta to which meta we discuss at 156 MeV.
Well, it is the temperature at which the hadrons appear to be in chemical equilibrium. I think within the model, that's all we honestly could say.
Within our model, yes, but in lattice QCD, there is a rather well-defined pseudo-critical temperature for the chiral phase transition, derived from, I think, 6 or 7 different measures, which is 156.5 MeV with an error of 1.5 MeV.
Yeah, this is this cyan band here, right?
Yeah.
Okay, so we have to move. Thanks a lot, Anton.
Thank you.
Good afternoon.
Pavel.
Yes, good afternoon.
Okay.
Can you see my slides?
Yes.
Okay.
So I will tell you when 5 minutes are left.
Thanks. Very good. So I appreciate this opportunity to present our program of open chart measurement in Na61 Shine experiment. So many thanks to organizers for giving me this opportunity. This is the outline of my talk. Short introduction to experiment, then I will show some physics motivation for open chart measurement, which were actually already very broadly discussed. So this will be just some personal selection. And I will also show performance of small acceptance vertex detector that we already built within the experiment and tested. We used it for pilot measurement. And the last point will be the proposal for the upgraded version, both of Vertex Detector, but also of the whole experimental setup and proposed measurement after long shutdown too. So the experiment, I think in this community, this Na61 Shine experiment is quite well known. Just few words about it. So it consists of 4 large volume TPCs. 2 of them, VTPC1 and VTPC2, are located in dipole magnetic fields, so that they provide tracking, and because the magnetic field, we can also determine the momenta of particles. We have a PSD detector that allow for some basic overall event characteristics. And newly, what was introduced is Vertex Detector, which is located here in this area. We called it SAVED, which is SAVD, Small Acceptance Vertex Detector, and it provides a precise tracking close to the target. It's located in the random field of the first dipole magnet. Physics motivation. So as I said, I mean, all these arguments as in the previous talk, but also in Na60 plus talk can be repeated. So just show me some personal selection. So this plot shows the model predictions for average number of CC bar pairs produced in central lead-lead collision on 100A GV over C, and you see that different models vary quite significantly in this prediction. So usually in models, you can calculate the probability that CC bar pair will be converted to J psi, and from the measured J-psi yields, you estimate within the model the average number of CC bar pairs. So this is the first argument to provide such measurement. How to measure CC bar pairs? So these values, given in percentage, just shows the fraction of the open charm quarks carried by the given species. It's based on the PSHD model predictions for 0 to 20 central lead-lead collision at 150 AGV over C. So you can see then even measuring D0, D0 bar, at D plus, D minus, we can capture 80% of the whole charm produced. And so already measurement of these four species gives quite good estimates for this average number of CC bar pair productions. But of course, these tables shows the whole the interest of the decay channels, which are under interest of the NA61 Shine program. This suppression as a signal of deconfinement is, I know that it was already discussed, but just let me say a few words about it. So this is this historical plot that shows anomalous suppression of J-psi. So this is the J-psi production related to Dralion production versus transverse energy, total transverse energy, which actually increases with increasing the level of centrality. And you see that the line represent the model predictions with assuming the normal nuclear matter absorption of J-psi. And you see that at low centrality or at low transverse energy, the model predictions are consistent with data, whereas for more central collisions, we see we see the suppression, which is called anomalous suppression, and was initially attributed to the signal of deconfinement. In 2005, the NA60 collaboration showed this plot that contains compilation of the old measurement of J-psi, but also of their measurement in indium, and they plotted it versus number of participants with this nice step, which was actually also interpreted as a signal of deconfinement. So the argument was that all models, all measurements just scales with this number of participants. So at given centrality, the condition if the produced medium are reached, so the quark-gluon plasma is created and the J-psi suppression is observed. However, the NA60 presented the same measurement, but with using the measured data, the measured result J-psi production is proton nuclei for the actually the right energy, the energy which is used here in J-psi. And the plot they presented looks like that. Yeah, so this nice scaling properties, actually this nice looking plot is turned to something quite different. So the conclusion was that there is still anomalous suppression observed but only in lead-lead. But there is very questionable whether the anomalous suppression is present in indium, and I must say that this plot look quite yeah, it's hard to draw any strong conclusions from this plot. So the later and quite recently, the results pointed out that actually the good reference to study the J-psi production would be not the Drellian or just production in proton-proton, but the good reference would be the average number of CC bar production. Yeah? So just study of J-psi over average number of CC bar pairs can actually capture the final state interaction. For example, what is predicted for the J-psi suppression. This actually was already discussed. This observable J-psi over D0 was already discussed in the previous talk. So you saw that it can be described as a smooth, relatively smooth, predicted as a relatively smooth curve within the statistical model. But I think the studying it experimentally is a very interesting perspective. Okay, so small acceptance vertex detector. Why we need vertex detector? So this sketch shows the idea behind the reconstruction of open charm of D0 mesons. So we have primary interactions. Actually, from the primary vertex, we have emission of many primary pions and kaons. And if we want to study decay of D0 to pion kaon channels, we have to find the secondary vertex of these decays and find the displacement between primary and secondary decay. The advantage of stationary target or fixed target experiments is that here we have a boost, the boost of the source, and the boost factor is on the level of 10. So with these 122 micrometers flight distance we go to the almost to the 1 millimeter, which is shown here when we stick to the top SPS energy, for example. So actually, there's this kinematic configuration favor fixed target experiments for such measurement. For example, as compared to collider experiments, of course, the collider experiments gain from the much larger cross sections. This is the picture of this pilot version of Vertex Detector. So you see that it consists of two arms, detection movable arms. They can be moved horizontally. They are located on the quite massive aluminum plate. You see the cover that allow to have a helium enclosure inside to reduce multiple scattering. You see the target holder with a LED target, which was integrated with the whole device. And if you zoom in the central part, you see the sensor integrated on the carbon support. So we used Mimosa 26 sensors. In total, for this pilot version, we use 16 sensors. They were located on 4 stations. And the goal which we managed to achieve is to demonstrate the tracking in the large track multiplicity and environment, the precise primary vertex reconstruction. The important issue was also that the possibility of matching between TPC and vertex detector tracks, that we can really do the matching and produce the global track. And we have also opportunity to search for the D0 signal. So the project was carried out by a group from Jagiellonian University with help from AGH University and works of University of Technology. The sensors were purchased Mimosa 26. HF sensors were purchased from EPHC, Strasbourg, but we also took a huge advantage from the carbon fiber support developed within Alice ITS project and readout system developed within CBM microvertex detector as a prototype version of the readout. Okay, so you see the profile of the primary vertex, I mean distribution of primary vertex reconstructed in the measurement made for xenon plus lanthanum at 150A GV over C, and the lanthanum target was segmented. It consists from the 3 lanthanum blocks squeezed together. Each block was 1 millimeter thick, and you see from the reconstructed primary vertices, we were able to see the profile of this target, and even we were able to distinguish on which block the collision happened. So using the sub-event technique, we were able to estimate the primary vertex resolution. And in the transverse plane, we got such values on the level of 1 micrometer. And in longitudinal direction, it is 15 micrometers. Okay, so first we tested the background suppression procedure. I mean, already in this NA60 plus talk, this background suppression was discussed. We also involved our background suppression procedure, and we tested it on reconstruction of K0 short and the lambdas. The strategy is, I mean, we used four cuts to reduce the combinatorial background. This is the cut on transverse momentum, cut on track impact parameters. So we are checking whether the track is coming close to the primary vertex. Longitudinal distance of the pair vertex to primary vertex. The pair vertex means the secondary vertex. So this is this displacement between primary and secondary vertex. We also study the parent impact parameter. So if we reconstruct the parent trajectory, we can test then whether it comes close to the primary vertex, which should be actually for D0. And also DCA, which is distance at closest approach. So these parameters are actually ensured, if this is small, it ensures that 2 daughters which are in the pair actually are daughters of the same parent. And you see the results for this is invariant mass of 2 pions, two pions and 2 proton and pion, and we as in any 60 plus study, we haven't used the PID information. So this is just the pure combinatorics when we select the unlike sign pairs of tracks and associate the masses. Here we associate the pion masses to both tracks, and here you associate proton and pion, and you use the two-mass hypothesis. But of course, depending how you associate the masses, you account for lambda or lambda bar particle. And you see the invariant masses, which I mean, in our case, we can observe the very nice peak practically without any background. So background is suppressed almost to zero. And then we apply the same procedure to OpenCharm. Here you see actually the parameters, the cut parameters which we used and these parameters were optimized in simulations. So these are really optimized parameters, and this is the results that we were able to obtain. So the total, this is for xenon lanthanum, 158, 0 to 20 centrality, and the events that survive all the standard and the 61 shine cuts is almost 2 million. So this is for 2 million event statistics, and what is plotted here is invariant mass of k-pion pairs. Also, the PID information was not used. So DDX was not calibrated yet. We are working on this also to include the DDX, and we expect the noticeable improvement. The overall efficiency of reconstruction that can be determined from simulation is 90%, which we think also, I mean, this is not the state of art. We also are working to improve it. But what was quite important factor is the detection, the sensor detection efficiency.
Are left.
5 minutes left. Okay.
Yes.
The sensor efficiency. I mean, this efficiency was let's say reasonable, above 90%, close to 95% for most of sensors. But if we require to have a signal on at least three detection stations, so we need 3 feeds, then the efficiency for detection of the track is in Vertex Detector was about 80%. Okay, so upgrades and proposed measurement beyond LHC. So the NA61 shine actually passed the upgrades. The main effort is dedicated to TPCs, which will get the new electronics and will allow to increase the data speed, data rate from the former 80 hertz to 1 kilohertz. So there will be more than factor of 10 increase in the speed. We will upgrade all subsystem also. Projectile spectator detector, time of flight detector will have a new data acquisition system, but of course for OpenCharm this important. The important is upgrade of Vertex Detector, and in the new detector we will replace this Mimosa sensors by Alice ITS. Alpine sensors, the sensors developed within Alice ITS project. So we will replace 16 Mimosa sensors by 46 Alpine sensors, because this Alpine actually has a larger surface. We will increase the detection surface from 32 centimeters squared to 190. And we will use reuse the most of the infrastructure of the current detector. What is important here in Alpine, we have much lower heat occupancy, the dark heat occupancy, and also much significant, much improvement in time resolution, which is also important when we want to run with higher data rate. So this is the requested open charm measurement for these years, which are indicated here. So we requested beam for lead at 100A GV, and we account to collect 250 million events. And based on our simulation and estimates, we foreseen to collect these amounts of D0 plus D0 bar and D plus D minus. This measurement will be spread over 3 years, and this table shows what are our predicted yield versus centrality. And the anticipated results. So these results come from simulation. So this plot shows the generated YPT distribution of generated D0 mesons, and this is after the detector filter. So these are reconstructed and applying also the background suppression cuts. So this is our final expected results. As you see, we lost something at the backward hemisphere, but still we can quite nicely. We have the good acceptance, and this is quite symmetric around 0, around the central rapidity value. Okay, so going to my summary. So NA61 Shine open charm production measurement started in 2017 with small acceptance Vertex Detector. First physics results await validation. So we already make some effort to turn this D0 peak to the physics results, but they still not reach the let's say preliminary stage. So I'm not showing this result. And after long shutdown 2, the high statistics data taking with upgraded detector is proposed, and the results from high statistics run are expected to distinguish between many existing models. Initiate the measurement of collision energy dependence of open charm yield, and verify signal of the QGP formation by measurement of centrality dependence of charm production. So thank you very much.
Thank you very much. Questions? Enrico.
Hello, thanks. It was very nice and informative. I have maybe a comment on your first, one of your first slides where you quote, let's say, a wide range of possibility for the CC bar multiplicity. I believe that most of them can be already constrained by indirect measurements that were performed in the Daimyon sector by NA50 and NA60 at top SPS energy. So some of them might be, let's say, compatible, but for some of them, I believe they are not compatible. They cannot be compatible because the spread is too large. But then
I agree with you. I mean, from the indirect measurement in Daimyon.
Yeah, but then let's say connected to that, in your slide 25, you give an estimate, and so maybe I missed that, and you have said that. But which kind of hypothesis you made on the open charm protection?
We use the hadrons, the PSHD model predictions. So
PHSD.
Yeah,
okay.
Yeah.
Okay. Thank you.
Other questions?
Hello. No, I was curious about the PID capabilities. So you mentioned that you will use new TOF detector what is the resolution that you plan to have?
Time of flight detector.
Yes, time of flight.
Yeah,
Yes.
I haven't speak much about it. Yeah,
Yeah, that's why I was curious, because I read the new time of flight detectors, and yeah, I was curious to know what is.
In the current system, the old system we used just the scintillator detectors, yeah, the photoscope, but this will be replaced by MRPC detector, and probably there will be some the timing improvement in timing, but really I'm not really familiar with the parameters, but I think they will also cover the larger area. So this is actually for OpenTram is important to because these former time of flight were just covering the relatively small phase space. So for OpenTram physics, we mostly based on DDX information from TPCs, but of course this time information will also be used, but I don't think it will be the critical for OpenTram measurement. Like in, for example, in A60 plus, they use this rather to skip to not use the PID information, but they rather based on large statistics. Yeah, so this is also very impressive when one can estimate what one can achieve just by the huge statistics and measurement only the momenta and trajectories of particles.
Yes, it's a different philosophy. Okay, any other question? I don't see other questions. So let's thank again Pavel. We can move to the next talk by Robert Pizarski.
Good evening. Can you see me?
Yes.
Yeah, hear me? Very good.
You can start.
Thank you. I'd like to thank the organizers for the opportunity to speak today. I very much wish that I could have come to Trento again. I wish actually being at a Department of Energy lab that I could go anywhere, including into the lab. But I have to say, I feel somewhat intimidated after hearing all of these talks on the really beautiful experiments that are necessary and ongoing at lower energies, and is clearly the new frontier in our field, or one of the new frontiers. And so I'd like to talk today about two ideas. One is admittedly rather speculative, and something which has arisen from recent results from the lattice, and in particular at the recent lattice conference. And this is the idea that the axial U1 symmetry may be approximately restored at the chiral temperature. And let me say at the outset that this is a very controversial topic, and it's something that the lattice has no consensus about at the present time, but it's really something very different from what any of us would have expected. And so it's worth thinking about the possible consequences if this did turn out to be true. In particular, based on old work that I did with Wilczek, that if the axial U1 symmetry is approximately restored, there may be violations of a principle which we think is well known and accepted, and that is isospin symmetry. And this is isospin symmetry in the simple basis that the ratio of the neutral to charged pions is not what you would expect. And related quantity to measure would be the ratio of the eta to the pi naught. Now, I recognize that this workshop is about electromagnetic probes, And basically what I'm going to be talking about is that it's worth measuring. Both of these particles are measured through photons, and to measure photons at very low transverse momenta. I'm also going to give you a brief argument as to why, even if the axial U1 symmetry is approximately restored at the chiral temperature, that it may be different at non-zero chemical potential, moving out as you go down in the square root of energy. As I said, this is a very speculative idea. The other is work which I've done recently with Semyon Valgoshev, Fabian Rennecke, and Alexei Tsvelik, and this is the idea of a Mote spectrum, which can arise as you go down to low temperature and non-zero chemical potential in the phase diagram. And here the idea would be, at a critical endpoint, the fluctuations by necessity are largest at zero momentum. And with such a Mote spectrum, the fluctuations would be largest at non-zero momentum. So if you could measure carefully enough, this should just slap you in the face. The difficult part, and this is the take-home measure that I'd like you to remember, is that it's really useful to think about measuring as low transverse momentum as possible. A speaker this morning mentioned that hydrodynamics works well for particles at low PT. He was referring to momenta of hundreds of MeV, where that's true. I'm suggesting that it's worth thinking about measuring down to momenta on the order of tens of MeV. As Li-Xuan mentioned the other day, the beam energy scan will go down to 60 MeV. Okay, well, let me review for you what the axial U1 symmetry does. This is very well known, but I just established notation. So we have some Lagrangian of Goldstone bosons, and this is the chiral symmetry is broken by a mass term. So you have the mass of the up, the mass of the down, and the mass of the strange. Now the mass of the up and the down are very different. And the up is like 5 MeV, the down is like 10 MeV, but these are both much less than the mass of the strange, which is something like 100 MeV. Now the anomaly term, if you form a field phi, which as I write is like Q bar left, Q right, this is like the determinant of phi. So it's invariant under the SU3 left cross SU3 right symmetry, but it violates the axial U1. And it has some coefficient which is proportional to the fluctuations in the topological charge, trace of the gluon field strength tensor times its dual quantity squared. And what this does, as we all learn in our elementary courses, is that this makes the pion, the eta, and the eta prime eigenstates of flavor. That is, the eta prime is primarily a singlet under SU3 flavor, and the pion is composed of UU bar minus DD bar, and similarly for the eta. This is a very good approximation. There is some mixing between the eta and the eta prime, but the eta prime is very heavy because this coefficient, I did not mean to do that, because this coefficient is very big in vacuum. But if you think about it, let me try to do this. If you didn't have this term, an observation which was first made by Wilczek, Gross, and Treeman is that something very interesting could happen. So let me first of all say the anomaly is always there. There's always only approximate restoration of axial U1. And as I said, in vacuum, this coefficient is big. The point is, what happens if this coefficient, as a function of temperature or chemical potential, becomes small? Well, then, in that case, you just have to look at this matrix. If you just look at this matrix, you would say, why should this lower right-hand corner choose to be a singlet of flavor? This thing should just line up. It's a 3x3 matrix. Let's just consider the diagonal elements. And then, therefore, the pi naught should just be pure UU bar, and the eta pure DD bar, and the eta prime pure SS bar. That is, instead of SU3 flavor, they're mass eigenstates. And this is the basic origin of isospin violation. If the axial anomaly is approximately restored. It's just this simple matrix exercise. Notice too that the pi plus and pi minus, by necessity to have the proper electric charge, are U bar D and D bar U. So this difference will be where isospin violation will arise from, because MU is not equal to MD. And this is what first motivated the work of Gross, Treeman, and Wilczek. And so you can ask, but why should this happen? Isn't that unnatural? And this was certainly the prejudice until very recently. I don't think any of us really expected this would happen. But it has consequences for the phase diagram. This term breaks the axial U1, as I said. And for three flavors, it's a cubic invariant. And in the chiral limit, it's going to drive the transition first order. It's just like liquid gas. You have a cubic invariant, you can't flatten the potential, it's going to be curved, you're going to get first order. So the prediction from mean field theory is that there has to be a corner. This is the plane of mass of the up equal mass of the dom versus m strings. This has to be first order. It's very hard to understand how that could not be first order. Well, unfortunately, as with other experimentalists, they don't listen to what theorists tell them. This is two graphs which I took from a very nice talk by Lahiri at the Lattice meeting. There are two results by his collaboration, including my collaborators at Brookhaven, RBRC, and Bielefeld, in which they claim that the axial U1 symmetry is strongly broken at the chiral transition. On the other hand, the Japanese lattice collaboration, using a different formulation, finds that it's very strongly approximately restored. Not exactly, but to a very good approximation, approximately restored. Now, this comes down to a difference of techniques. These are using highly improved staggered quarks, and so they would argue, well, that's very good, we improve. This is using Mobius domain wall fermions, where you have an exact chiral symmetry, but they don't improve the rest of the action. So it's clearly something that's up in the air. But there's other work by Kuteri, Philipson, and Sciarra, in which they make the absolutely astonishing claim that in the chiral limit, the chiral transition is second order for three flavors or greater. And as I said, this is really quite unexpected. For four or more flavors, based upon the analysis by Wilczek and myself, this would mean that you'd have to have a new fixed point not seen to order epsilon in 4 minus epsilon dimensions. That could happen. This can be tested by conformal bootstrap and other very sophisticated theoretical techniques. But what I find astonishing is that they're claiming it happens even for three flavors. And this must mean that this coefficient due to the anomaly is very small. It's possible you can have fluctuations wipe out a transition you expect in mean field theory, but it then means that that coefficient is small. And if that coefficient is small, then it means something interesting could happen. It's certainly most exceptional, even for on the grounds of a phase transition. I know examples where it happens in 2 dimensions, but not in 3. Okay, so it's very exciting. It's very up in the air. What could be the experimental consequences? Well, as I said, because if axial U1 is approximately restored, instead of being flavor eigenstates, they're mass eigenstates, and the pi and the eta would then manifest isospin violation. Now, I looked for results from Star or Phoenix. It's, to be honest, it's a very hard measurement, and I'm not underestimating the difficulty of the measurement. You measure pi naught from gammas, you measure pi plus, pi minus in other ways, but there seems to be an approximate suppression that is not equal to 1. The error bars are large. Star and Phoenix don't agree. I'm simply suggesting that it's something that you would assume cannot be violated, may be violated in heavy ion collisions in certain circumstances, and that consequently it's well worth thinking about. As I said, if the eta becomes pure dB bar instead of an SU3 flavor eigenstate, the ratio between the eta and the pi naughts should change. There's data on this from Phoenix, excuse me, but it's at 6 GeV in transverse momentum. And so the other lesson I want you to remember is that it's really worth thinking about going down in momentum to see if maybe these ratios change in a way that we hadn't expected. Okay, let me then mention some results that I obtained with Fabian Rennecke in the past few years. We looked at the standard result for dilute instantons. And in this case, if you're at finite temperature or chemical potential, then this is simply screened by the Debye mass. The instanton, which carries topological charge, has both electric and magnetic fields. And so if you get a Debye mass, that tends to suppress instantons. This is an old story. Our point is simply that this coefficient, if you look at the coefficients between mu and temperature, there's automatically a factor of pi. And this is the chemical potential for the quark. If you assume that the fluctuations in vacuum are dominated by instantons, which admittedly is a somewhat preposterous assumption, this is a huge factor. This means mu quark, if you take T on the order of 150 MeV, you're up to something like 700 MeV in the quark chemical potential. This means that even if the axial anomaly is small at 0 chemical potential in the chiral transition, perhaps once you go out in chemical potential, it again becomes large as it is in vacuum. And you don't see axial U1 restoration until much higher temperatures. Much higher chemical potentials. Again, the moral is to measure the ratio of pi naught over pi plus pi minus and eta over pi naught at low PT, really low PT. Okay, this is easy for a theorist to say, but it's basically, as I said, I'm not underestimating how difficult it is. It is very difficult, but it's worth testing general principles. Okay, let me then go on to the second section of my talk. And this is the idea of how things might change at non-zero chemical potential in the phase plane. In his opening talk, there was a very nice picture of the phase diagram by Kabiba and Parisi, where it was a simple semicircle. And it's been known for about a decade that this could change in soluble models of the chiral transition. This was work done by Gaksha Basar, and there was a long series of work by Michael Thies. They looked at the Gross-Neveu model in 1+1 dimensions where you can solve it. And the point is you find two phases. At low temperature, you have a phase where you break chiral symmetry, a phase at high temperature chemical potential where you restore it. But at low temperature and large chemical potential, there's a kink crystal. And what this crystal is simply where psi bar psi oscillates in space. And this is directly analogous to pion condensates. So you can construct an effective theory for this. It's the usual kind of ON vector theory. So you have kinetic terms, you have some potential term. And the thing that's interesting is that in medium, at non-zero chemical potential, the simplest way of understanding this kind of kink crystal is if you add higher derivative terms in space, not in time, that's prohibited by causality, and then you add compensating terms to stabilize the theory. This is actually very natural, even if you didn't have these exact results. To get a critical endpoint, what you have is this quartic coupling here flips sign at the critical endpoint and is then negative, which gives you a first order line. What we're suggesting is you have what's known as a Mote spectrum where Z is less than 0. You have to have this M squared finite in the same, for stability in the same way you have to have higher order interactions here. Okay, so what does a Mote spectrum look like? Well, what it is you have some mass gap But as you go faster, it gets easier until, in fact, at some critical momentum, you have minimal energy. This is for z less than 0, and then it goes back up. And this can only be true for collective modes at low momentum. You have to go to the usual dispersion relation at high momentum by relativistic invariance. But you can have this momentum. And our point is simply that the fluctuations could be maximum at critical momentum not equal to 0. Again, this critical momentum is undoubtedly on the order of m pi. It could be less than m pi. So you need to think about measuring at very low PT. But this is what's necessary for the critical endpoint anyway. So it's something that, while not easy, should be done. Okay. One can show that, in fact, if z becomes sufficiently negative, that you can have what's known as a chiral spiral. And this is directly analogous to a pion condensate. So the field squared has some constant magnitude, but as you go along in one direction, it oscillates between, say, the sigma and the pi naught direction. Now, for this to happen, you have to satisfy two conditions. Well, it has to be a minimum of the potential, and you have to have some condition that fixes this, the length of this spiral. And these are the conditions. Our point is that people have spent a lot of work looking at this, but that you can have this kind of spiral, but you don't have to. You can simply have z less than 0, which is the Mote spectrum. If you go in a certain range of parameter space, you'll also get this chiral spiral or pion condensate. And in fact, we argue that quantum fluctuations will disorder this, but I probably will just go into that very briefly. It's a statement that we claim that while classically there can be these chiral spirals or pion condensates, they'll be disordered by quantum fluctuations and form a quantum pion liquid. But I'm just going to flash through that. It's possible that this region with the Mote spectrum is very large. Here I show results from a functional renormalization group by Wei-Jin Fu, Jan Pawlowski, and Fabian Rennecke. They didn't calculate for chemical potentials to the right of where they find the critical endpoint, but they did find in a large region that you have this z less than 0, where you get a Mote spectrum. I might also mention that the region in which they expect a basin of attraction to the critical region is in the FRG uniformly tiny, less than 1 MeV. But that could be due to the assumptions and approximations of the functional renormalization group. All I want to point out is that in this diagram, where you'd see effects of the critical endpoint is very small, but this blue region is very large. And as I said, they haven't computed in this pink region. Okay, so what would happen there? Well, you have this kind of funny propagator. And I've chosen illustrative parameters and effective mass of 20 MeV, which admittedly is very low. And this mass here is like 1 JeV. So this is not meant to be definitive. In fact, you absolutely have to match onto the usual spectrum, because if you go to a boosted frame, as in a blast wave parameterization, you'll find solutions with imaginary energy. But for these choice of parameters, this gray curve is the usual pion dispersion. If it's z is half, this is what it is. And then as it becomes negative, it just gets flattened. And so the point is you get fluctuations moving out from being concentrated at this point to non-zero momentum. You can see this from the single particle spectrum. Clearly, if you have this change in behavior, well, let's take the most extreme case. If z is relatively large and negative, then you'll find a peak at non-zero momentum for the single particle spectrum. And notice, however, this is the usual spectrum. Okay, it's peaked at non-zero momentum, but even if we go to z of a half, it becomes a much broader spectrum. Now, of course, these are momenta, again, on the order of, 100, 200 MeV. It's a very difficult region, but it should give a characteristic signal of a non-thermal spectrum. What we then did is we did a blast wave parameterization. We used a standard Cooper-Frye formalism. So sigma here is the blast wave. P naught hat and P hat squared are the momenta in the boosted frame. And as I said, even for relatively low boost velocities on the order of 1/3 the speed of light, you can obtain imaginary energies unless you take this only in a limited region. What we did is to take it up to where the momentum is less than 2 pi. And we took the following parameters for square root of S over A of 5 GeV for the temperature and the chemical potential. Okay. You then have to, our basic idea is that if you have a critical endpoint, you'll have genuine multi-particle correlations, as pointed out by Rajagopal, Shriyat, and Stefanov. But if you have a Mote spectrum, you can still have correlations simply because of their propagation in the medium. So we did this in terms of 2-particle correlations. And so you have a product of the single particle densities. You have an integral over the blast wave. And what you have to do is look at fluctuations in the thermodynamic variables, which are here the temperature, the chemical potential, and the boost velocity of the medium. You then expand in quadratic order and calculate the connected part of the distribution function. This is a standard exercise that's familiar with from Landau and Lifshitz. We are using a generalization due to Stefan Florschinger, where he generalizes to the case where you also have a boost velocity. I won't go through the details here. What you do is you write down the typical partition function for the fluctuations involving a vector nu hat, which is the normal to the hypersurface. You have to do some computations. I simply show this to illustrate that we did do some work. It involves the usual parameters you'd expect, the entropy, the derivative with respect to temperature, this normal to the hypersurface, and so on. Little n is the number density. You do this calculation, and what you find is the following. You have the 2-point function for the connected 2-point functions, and it's an integral over the hypersurface times these quantities and derivatives of the mass condition. We then computed this for the most optimistic case, and what we found is the following. Well, this is the usual term, and there's not really any correlations for the usual term. So we calculate, this is a plot in each case of the 2-particle connected function divided by the product of the single functions, and that it's really very flat and boring. This is the transverse momentum of one particle, the transverse momentum of the second particle. It's flat and extremely small, 1 part in 10 to the 12. So there's not really any reason why you would measure it. If you have a Mote spectrum, on the other hand, you would expect the fluctuations to be concentrated, again, about the minimum in the energy dispersion relation, which is in this case about 120 MeV. So you see this big peak, and more to the point, what's interesting is that it's a much larger peak. Admittedly, it's still 10 to the minus 8, but it's 4 orders of magnitude larger. And so the point is, again, that if you can measure correlations, and in particular 2-particle correlations at low transverse momentum with accuracy, that you could see an absolutely unexpected experimental signal. Okay. In the few minutes remaining, let me mention a comment that people have spent a lot of time looking for these chiral spirals. This is work that's been done by Michael Bubala, Carignano, Monarelli, and many others. But we were able to prove the following theorem, and I won't go through it in detail. I'll simply say we take a theory where you have arbitrary powers of higher spatial derivatives, an arbitrary potential, and we assume that you get this kind of chiral spiral under the technical assumption that its magnitude is constant. And what you can show then, well, you calculate the effective Lagrangian, you put this in, this is what you get, and you have to vary with respect to the length of the spiral for the momentum K naught and the magnitude of the condensate. So you do that, and you do this for n bigger than 2, so for O4, as for 2 light flavors. And what you can show is that, first of all, you have 2 conditions. If you calculate the inverse propagator for the Goldstone bosons, now this is not the phonon, it's the Goldstone bosons, that this is equivalent to the condition that the Lagrangian is minimum with respect to the magnitude of the condensate. Okay. And if you further require that it's calculate the variation of the inverse propagator, again for the Goldstone bosons with respect to this momentum, you find that that's proportional to the variation of the effective Lagrangian itself. What this shows is that for the above chiral spiral, that the energy of the Goldstone modes vanishes at this non-zero momentum. This is easiest to see pictorially. We know that if we have transverse modes, there's going to be Goldstone bosons somewhere. What we found in this model is that it occurs at a non-zero momentum. That is, there is a zero due to the Goldstone bosons, but it's exactly at non-zero momentum. Now, why is this important? Well, it's because if you calculate a tadpole diagram, well, you're used to calculating this. It's usually pretty innocuous, but if it's at non-zero momentum, most of this gets taken up by the non-zero momentum. You then have a linear integral upstairs over the deviation from this minimum. And if you look at this factor, it's the square. And so you have 1 power upstairs, 2 power downstairs, you get a linear divergence. And we conjecture that this is a theorem for all chiral spirals, that while they may be valid solutions classically, if there is a continuous symmetry that you violate, that it's disordered by quantum fluctuations. I must say, to be honest, I've made this technical assumption that this magnitude squared is constant. But we believe it's a general theorem, and it would be very interesting to test this in other models. Physically, what's happening is that you have this chiral spiral as you go along in some direction in space, but if they're Goldstone bosons, their linear infrared divergences disorder it. As I said, we can't prove it in general, but we believe it's true. If it is true for any Goldstone bosons with a continuous symmetry, it's useless to look for classical chiral spirals. And I might mention this excludes the Gros-Neveu and chiral Gros-Neveu model, which have a Z2 and O2 symmetry. You need something bigger than O2. I have some time left, but since it's late in the day, I'll simply show you what we were able to establish. What we were able to establish for an ON model at large N is that, in fact, you have a symmetric phase. What happens is that here, where you have zero mass gap classically, that one is generated dynamically at large N. This is simply by equating an effective mass squared to a tadpole diagram. This is then the tadpole diagram where this is dynamically generated. This integral is valid in 3 dimensions, which is relevant for the static mode at non-zero temperature. What we can show is that if this coefficient z is large and positive, that you simply have a perturbative correction to the mass. As z goes to -infinity, though, you get a unusual solution. It looks fine. It looks, well, I'm a factor that's negative. Okay, it's the mass squared that matters. But in fact, if you look at the detailed solutions, as I said, what you get is you get an effective mass gap. And if you look at the correlation functions and you go ahead and solve it, you find the usual exponential fall off as you'd expect but there's also an oscillation. And we term this a quantum pion liquid. Instead of getting just exponentially damped correlations, you have an exponential times a oscillatory factor. Oh, that I did not mean to do. Okay, well, I'll just leave it like this. Yeah, okay, I skipped ahead one slide. I did, oh, okay. Let me go to the end. We term a quantum pion liquid. And I know I have some time left, but as I said, I won't bore you. The above is for non-zero temperature. You can show that it's also true at zero temperature. Instead of getting a linear infrared divergence, you get a logarithmic. And so the mass gap that you get tends to be much smaller. This is a possible relevance to neutron stars. And I argued that it might generate a spike in the speed of sound of nuclear matter due to specific coupling for the omega mu meson. That's somewhat afield, and since it's late in the day, I'll take advantage of your patience and stop there. As I said, besides all of the rest, I simply want you to be remember that there could be very good reasons for measuring down to very small transverse momentum. I realize this is very challenging experimentally, but I think it could yield really unexpected consequences. And with that, I'll thank you.
Thank you very much. Questions?
Hi, Rob. Thanks for the talk. Can you go back and show this FRG calculation?
Yeah.
With the Mote region.
There is. Can you mute the microphones from outside, Volker?
Let's see. You mean
Pavlovsky and company? Yeah, this one.
Yeah.
Can you say how this Mote region was determined there?
They just looked at the pion propagator, and they found that Z was negative. But it does not indicate a chiral spiral. That's why I discuss things later.
No, sure.
Yeah.
So this is some kind of precursor, would be some kind of precursor for a chiral for a pion condensate below the critical point, isn't it?
Yes. It would. It's a necessary but not a sufficient condition. Absolutely. Yeah.
Hi, Rob, Joachim. Thanks for the inspiring talk. So the low momentum, you said something like 100, 200. So in hardest, we have pions down to 80 or 60, depending on charge. But there is, of course, a Coulomb effect, which one would have to carefully consider taking ratios. So how big an effect you would guess there is?
I mean, at high energies, so where the baryon chemical potential is hard, it's at least intellectually cleaner testing isospin invariance. I recognize at lower energies where you have a net isospin to begin with, it really is difficult. So I haven't done a detailed analyses. This work from the lattice is very recent and I think very unexpected. So I don't have a detailed analysis, unfortunately, for which I apologize. But it's got to be much harder. I mean, really, because you have a net isospin, right? You have the nuclei. They don't get swept out. It's hard. So thank you for the comment that it's inspirational. You could also conclude it's just pie in the sky. But think that it's worth thinking about such things. Well, it's late in the day. Are there other questions?
Shall I try? Yeah. Rob, can you hear me?
Yeah.
Yeah. Hi, Rob. So coming back to equilibrium properties, do you have suggestions for any model where one can observe these funny pion propagators other than QCD? So something that one can simulate at finite baryon density. So suppose I do finite isospin density or two colors, would I be able to see something confirming or better understand it?
Yeah. In my last work with Valgushev and Svelek, we suggested gross. You need a kind of gross niveau model, but where you have a symmetry larger than O2. And you could get this either in 2+1 dimensions, where you have to take care because the fermion mass term is parity odd, or even in 1+1. But you have to take a larger gross niveau model than people have considered. It's basically, you'd have to take something like psi bar isospin matrix A psi quantity squared. So the symmetry is not just Z2 or U1, but is really a SU2 or higher symmetry. Oh, I apologize for having my microphone on. There's an echo. Oh, well.
There are two questions from outside.
Yeah.
Volker?
Yeah, Rob, very nice, interesting talk. And looking at this dispersion relation reminds me of the good old days when we played with piezo bars. Of course, this is different physics, but the phenomenology is probably similar. So one thing.
Wait, isobar, what? How is
piezo bars, the pion interaction with isobars in matter, you also got a dispersion relation that you have a minimum and things like that. That's 20 years ago, 30 years ago. Anyway.
No, because that's like a precursor of isospin condensation.
No.
That's
another collective mode. You have this, people streamed up with pions. But so the phenomenology, two things. First, you have a minimum in your dispersion relation. Does that mean your modes there are superluminous? And the second
option. No, they don't travel faster than the speed of light.
Well, the dP by dE is certainly infinity there, right? But the
group velocity.
Yeah, right. So then the other thing, if you have a dispersion relation like that, you can actually emit these modes similar to Cherenkov radiation. Have you thought about that?
No, I haven't thought about it, but your comment reminds me of when I talked to Larry McLaren, and he says, so if you take one of these particles and you start running, it gets easier.
Exactly. No, but they radiate just like Cherenkov radiation.
Yeah.
So you
can I haven't thought about
a cone.
No, that's,
right? Of these pions or whatever.
Yeah, no, that's a good suggestion. No, I hadn't thought about that.
And if my final question, your two particle correlation function, this is I assume a true subtracted where you subtract the square of the means, right?
Yes. It's the connected
the correlation.
It's really kind of trivial because, the fluctuations in each are at non-zero momentum.
Yes.
So it's really we subtract it. It's the connected
part. Then it goes away, right? I mean, so that's why I'm asking.
No, that's not obvious. You have to go through this exercise, and it's not obvious. It's because they're emitted from the same hypersurface, if you wish.
Okay. All right.
It's not obvious, and I didn't think it would be true, and Fabian kept saying you'd get something.
Okay, so that would be something for a coffee break, which we unfortunately don't have.
Yeah.
All right, thanks.
But it's not obvious. It's not obvious. That's why I showed this complicated looking figure.
Question from outside.
May I ask my question?
Yep.
Okay. So
Archie,
I have the following question. I understood that you need pions as Goldstone bosons, according to your the last discussion concerning the pion quantum crystals. But in the phase diagram from the Jan-Pawlowski and his collaborators in FLG, the blue region with negative Z factor appears in restored phase.
In the what phase?
In restored phase, not broken phase. So I wonder.
No. Yeah, no. But that's the point of why I went through this thing, that you can have a phase where Z is negative, but you don't get a condensate. It's part of the symmetric phase.
I see.
It's something that it took us a while to understand. When most people think about it, you're right. They have Z less than 0, and it's in the broken phase. Phi naught is 0. This Mote spectrum, you can have even in the symmetric phase. It's kind of weird. But there is a region in which it can arise.
I see. Okay. Yeah. Thank you very much.
Yeah.
Let me start. So I'm going to talk about Hades measurement of baryon electromagnetic transition form factors. So I go back to dileptons. And let me just take some. Okay, it's better. So I start with some motivations which we relate this time-like baryon electromagnetic transition form factors to the topic on this conference, namely emissivity and low mass dileptons, particularly raw based on immediate spectral function. So I will show this relation. Then I will present you data which we collected with Hades on baryon electromagnetic transitions in nucleon EPN reactions, and then do some perspective for future. So just to remind you, this was shown several times on this conference. We have this remarkable success of the description of low mass dileptons using thermal models and the spectral function of a raw meson, which is strongly modified in hot and dense nuclear matter. So here I show you, I pick up examples from NR60, from STAR and Hades, spanning the big range of beam energies. And as we could all see, this data are very well described by the thermal models, which imply the broad modification of the raw meson spectral function. So in principle, all this yield is saturated by the radiation from the raw. And important part of this calculation is this spectral functions, which are calculated with this hadronic approach, where the in medium raw meson propagator is modified by several contributions, like those related to the scattering of the interaction of the raw meson with the baryons, modification of the pion loop in the raw meson self-energy, and scattering raw on mesons. So, and we know that particularly these interactions with baryon do play a big role in the melting of the raw meson, as shown on this graph here from Ralph and Wambach. And here, I mean, if one cuts this diagram where the raw couples to the particle Hall state, where the raw meson, when the resonances are included, this diagram can be cut, and then it's simply related to the simple elementary process, which is called Daly's decay of the baryon resonance, where the baryon resonance goes transition to the nucleon, and the raw is an intermediate field connecting to the E plus and minus in the final state. So these processes are were never actually measured before, and therefore they are quite important in our view to be addressed in the special measurement program, which is aimed in the measurement of the Daly's decays. And that has been done in the HADES, and the basic thing which is the matter of interest here is the measurement of this transition form factor of the baryon resonances, and this is achieved in the measurement of the Daly's decay in the time-like region, but it can also be addressed in the space-like region by the scattering of the electron on nucleon, and such experiments have been performed in many facilities. But what you can see that in the time-like region, one of course expects that these form factors which determine the coupling of the photon to the baryon is strongly influenced by the presence of the vector mesons. While in the space-like region, one sees in principle the tails of the raw meson. And in other kinematical region related to the annihilation of the E plus and minus, one can also investigate transitions of the E plus and minus to resonance states, but there is little data on this, what we are interested in. So this Daly's decay is related to the transition form factors, which can be written on example here of the delta Daly's decay in a way that you have some, so this is a partial differential decay width, which is given by some function, which could be calculating from QED, assuming that the objects involved in these transitions are point-like. And then we have a set of transition form factors here, magnetic, electric, and the Coulomb, which depends on a Q square. And we are actually in HADES not in a position yet to disentangle all of this contribution. So what's actually what we are measuring and what I will show you is some effective transition form factor, which is the sum of all these three contributions. But much is known actually from the space-like region. So one example that I show here is the transition of a delta to the real photon. And here you see that here in the transition, which is related to the spin flip, is from the delta to n, to the nucleon. It's actually described in a high Q square very well by the transition between on the quark core, coupling to the quark core, but in the low Q square, a big role plays this famous meson cloud. So there's a certain list of models which takes the advantage of existing of this data and try to reproduce the data in a space-like region and then extrapolate it in a time-like region. And some of its models will be also shown in my presentation today. So what we actually measuring in HADES is transitions in proton-proton and pion-induced reaction where the resonance is created and then it decays into this final state to nucleon and E plus and minus. But we use always the exclusive kinematics, namely that all final state particles are exclusively reconstructed. Therefore, we address here the particular, really in a clean way, the decay of the resonance. So these reactions I will show you in next. So I start with PP reactions at low energy at 2.4 GeV square root of S. And this is really a very nice clean reaction where the delta is excited almost entirely. The excitation of the final state, which we are interested in, namely proton E plus and minus, is related to the delta Daly's decay, and this is has been proved and demonstrated in our analysis, because we take from one side we measure the one pion production, and also in the same experiment we measure dielectric production. So for measuring the pion production, we have a control on the resonance excitations. And here our working horse is to extract the cross sections for the resonance excitation is a partial wave from Bongacina, which is one of main working horses in the baryon spectroscopy. So the method includes the decomposition of the cross section in the partial waves, based on the measurements done with several experiments. So this is energy-dependent solutions. And the accuracy of a method really depends on the number of the reactions which are fitted at the same time. So in the hardest, with the hardest data were fitted together with 13 other data measured elsewhere. So here you see the result of such a decomposition of a PP reaction, where you see that the delta as a function of square root of S, that the delta indeed dominates the cross section, as well for channel with a charged pion and a neutral pion. And here you see just an example of invariant mass distributions of a nucleon and pion, and angular distributions of a nucleon, of a neutron, and here of a proton, a centrum of mass, and the quality of a description of the data. So having this delta resonance under control, we could look to the dielectron decays, and here you see the invariant mass distribution of the dielectron pairs. So above the pi0 Dulles, you see clearly the kind of Dulles distribution from the delta Dulles decay. And this is compared now to several models, particularly those which were tuned to the spacelight data for the delta decay. And this is a model of Teresa Peña and Ramalho, where two contributions do play a role. So the coupling of the photon directly to the nucleon, to the quark core. So this is this contribution. And then there is another contribution related to the coupling of the photon to the pion cloud, which is just nothing else as this pion emitted between the delta and nucleon. So the pion cloud contributions plays here an especially important role. So you can better see this in plotting the ratio of this invariant mass distribution to the baseline, which is a QED reference, calculated assuming that this is a point-like transition, and transition between point-like particles, so which is this blue line. And then if you plot the ratio, you see the data points really show some enhancement, which we do expect for the contribution of a vector meson, so rho meson in this case. And here you see the comparison to the component of this model. So the total is this blue line, and the contributions from the pion cloud is, as you can see, shows the stronger rise, which is related to the coupling of the pion to the E plus and minus. There's nothing else as an impact of the pion electromagnetic form factor. What is also nice to see that the angular distributions of the leptons in the rest frame of the virtual photon shows a very anisotropic distribution, which is actually expected if the photon is transferably polarized. And this angular distribution can be fitted, and this index, the coefficient parameter B, is very close to 1, which is exactly what one expects for the dominance of the magnetic of the transition in this transition form factors of a magnetic contribution. So in this measurement, we have also measured for first time the branching ratio for this transition. So that is a kind of a first measurement of the effective transition form factor for the delta Dulles decay. So going to PN, this was already discussed on the Joachim talk, that I mean this delta excitation is not the only source which contributes to PN reactions. So one do see significant contributions from the emission from inline from exchange charge pion, and this is really something very different as compared to PP reaction. So the PP reaction, which is actually plotted here, the dashed blue line, is saturated by the delta Dulles decay, while in the PN reaction, we do see a really strong contribution from this inline emission. And again, that strikes what comes in here is the contribution for the charge pion form factor. And then the sum of these two contributions goes roughly through the data, as what's shown by the calculation of one boson exchange model of Ulrich model and Shyam. So this is also a very nice example. One can now look more in details to characterize these sources, and then look in there again to the angular distributions of lepton to the polarization of this virtual photon in this two invariant mass region, one which is, let's say, dominated by delta, and the other one in the higher mass region. And one see really a striking change of the pattern of the angular distribution, while in this lower mass region beyond the pi0, one do see this anisotropy expected for delta Dulles decay with a coefficient equal close to 1, while in this higher mass region dominated by the charged pion emission from the internal line, one do see indeed a distribution which is rather has an anisotropy parameter which is negative, close to 0.5, and that is actually quite nicely explained by the calculation done on 90s by Elena Bratkowska and others in the one boson exchange calculation, where they calculated this anisotropy parameter for the delta and also from a PN Bremsstrahlung. Here, as one can see, for the PN Bremsstrahlung, here with soft photon approximation, this B is indeed going as a function of invariant mass to the negative value. So this is actually also something which is expected for the raw meson dominate. So actually this measurement, actually we would like to continue with much improved statistics. So we handed a dedicated proposal on DP to the GSI PAC, and we hope that it some time would be possible to be measured. So going to the higher energy, we have made an experiment with the PP at 3.5 GeV, and here that was also shown here in Hendrik's talk. Actually, we had to use here the resonance model, so we just assume the incoherent summation of several resonances, and it's the starting point was this parameterization used in several transport model from TICE, and it was optimized in collaboration with the Gießen BOU group. Here, actually, the situation is much more complicated. There are several resonances, which you can see again in the measured one pion production. So invariant mass here we show invariant mass of nucleon and pion, charged pion and neutral pion. And here we do see that several resonances contributed, particularly the higher mass resonances. We were able to fit the spectra very well, as you can see, using the very simple model which applies some scaling of the cross-section with 1 over T, which is T is a 4 momentum transfer between the resonance and nucleon with some scaling. And the scaling parameter actually was found to be very nicely, which has a the scaling, this alpha parameter has a quite smooth dependence on the invariant mass. So this empirical parameterization was used, and then the data was very well described, and therefore we could have made an attempt to compare the measured E plus and minus distribution now to this resonance model. So you see these are the E plus and minus exclusive final state invariant mass spectrum, where you see the omega peak, but below the omega you see mainly the contributions from the resonance decays into the nucleon and the raw, and the delta is much lower. So the main contribution indeed comes for higher mass resonances, and the good description of the data could be achieved using our resonance cross sections. So this is what is called here the model 1, and the resonance cross sections were then multiplied by the branching ratio into the raw. And at that time, the branching ratios of the resonances were given by the PDG for the resonances which were most important here. So starting from 1520 to delta 1905. And this branching ratios at that time, the PDG, as you could see, were quite large. I mean, now we face the situation that most of this branching ratio are removed. So in principle, the situation for today is that these branching ratios are not known anymore, or not given, at least in the PDG. So that was the branching ratios which were applied in the transport mode and the TICE parameterization, while on the other hand, at that time, we're already available some upper limits for the branching ratios in raw from the Boncacina. You see that they were really smaller than those which were used which were in the PDG. There were also some fits performed by partial wave analysis groups by Klaas and Manley. So the situation was quite unclear. Nevertheless, the good fit which was achieved here was actually applying this smaller branching ratios of the resonances, which actually was kind of puzzling as compared to the branching ratios which were available in PDG at that time. So this and an additional important parameter here in the calculation is the mass-dependent decay width of the raw, which follows the vector meson dominance, so it's with 1 over m3 was here applied. But in general, situation was not satisfactory. I mean, one could see that this resonance is, I mean, one could see that spectrum of the resonances here in the invariant mass of the nucleon in E plus and minus, and the dominant contributions comes from around 1.5 GeV. So we decided to make a dedicated experiment with a pion beam to address the really the details of this decay of the baryon resonances into the E plus and minus. And the pion beams indeed has a lot of advantages with respect to the PP. So in a pion-induced reaction, this is really a formation experiment. So one excites the resonance with a given well-defined mass, and then one can measure E plus and minus in a two-body final set. So at GSI, we have a pion beam, which is a secondary pion beam. So we use the primary reaction as a nitrogen and beryllium target, and the pion intensity which you can get is around 2 to 3, 10 to 5 pions per second. You see the spectrum of the pion striking, which we can transfer to the Hades by a special transfer line. And then this beam can be used to measure the final state in the Hades detector. So what we first, we concentrated on the second resonance region where the 1520 is expected to be dominant, and we measured the 4 energy points, but we have used polyethylene target and carbon target. So it was actually the first and some pilot run, but it appeared to be quite successful. We could really indeed identify in a unique way this production of a E plus and minus, and this is demonstrated here. You see the E plus and minus missing mass above the pi0 invariant mass. So here you see the invariant mass spectrum inclusive on polyethylene target and on carbon. So doing the missing mass with E plus and minus above a pi0, one can see a clear peak coming from a neutral. So this is a really signal for this reaction. And this is here shown for the polyethylene target, for the carbon target, and the proton target. You see that the width of this peak differs between the carbon and the proton, and that is just due to the momentum distributions of nucleons in the nuclei in the carbon. So this width is entirely due to this Fermi motion of Fermi momentum of the distribution of the protons of the nucleon in this case. So this is well understood in the simulation, and that allows us to let's say to separate this quasi-free reaction E pi minus proton with E plus and minus, and this is shown here with this missing cut. We could really very well reproduce the pi0 peak using the known cross section, subtract it, and then what is remains is this invariant mass spectrum. So you see from a very first glance that there is indeed some enhancement going in the high mass as expected from vector meson contribution. So as in the proton-proton case, we have done some additional measurement of a 2 pion production here in 2 channels with the charged pions, pi plus, pi minus.
5 minutes left.
Which has this is a golden channel for the pion for the rho meson production, and here you see using the partial wave analysis, we could together with the other reaction channels, we could very well describe the 2 pion invariant mass distribution and extract the rho meson cross section. So the rho meson contribution is here shown by this blue line. So note that this is just below the threshold, so there is no rho peak, but the rho meson contribution has been here determined. And then using this for measurements, we could determine the excitation function for the rho meson. Here you see all channels which were so the decomposition was obtained for all channels contributing to 2 pions, so delta pi and rho and sigma. So the most important is of course for us the rho meson, which is the dominant contribution here in the pi minus pi0 channel, but pi plus pi minus is one of the contributions. So having this data, we could determine for the first time, I mean for the new PDG that went to the new PDG entry, the branching ratio of 12.2%, and for 1535 with 3.2%. So having that, we could go to the dielectron spectrum, and here in principle, the situation to get the E plus and minus spectrum, we could, one has to just, based on the pi plus, pi minus distribution, one can convert this to E plus and minus just by multiplying this ratio of the decay width to E plus and minus and decay to the pi plus, pi minus. So here for the partial decay width into E plus and minus, there are two actually models, which vector dominance model formulation, which are equivalent for the universal coupling constant, which is G rho equal to G rho pi pi. So this is a model formulated by Sakurai, which is very known in using heavy ion models, and so-called vector dominance model 1, which we call it here in this here VDM1, coming from Crowley and Tsumino, which actually has a little bit different construction. So it assumes, it allows also for the direct coupling of the photon to E plus and minus, and the coupling of the ρ2 photon. And the feature of these two models is quite distinctive, different dependence of the rho meson decay width. One is go 1 over m to the power of 3, while the other one goes to the m power, it go linear with m. So there is a quite different scaling of the mass dependence width of the rho meson decay. However, the second model was shown in several works by Freeman, also by Effenberger, that this model has two different coupling constants, one to photon, one to rho. So it allows independent to fix the branching ratios to n gamma and to rho, which otherwise in this other model are not really well described both simultaneously. So this, we have used these two models here, and the QED reference is given by the reaction gamma n to pi minus proton, which is also decomposed into the partial waves. And the contributions in these reactions are of the D13 and S11 are very well known from this decomposition, and also the cross sections. So here we have a bound on the real photon contribution, which could be converted to the E plus and minus. And this is our QED reference, and that will be shown in the later, knowing the well-known dependence on the invariant mass spectrum worked out by Krivoruchenko et al. So here you see the distribution of the experimental data now compared to the QED reference. So this is this line. You see that, of course, the data are really showing very nicely excess over the QED reference as expected. So this is immediately the sign of the vector meson dominance. However, if one look into more details and then compares this to the calculation based on vector dominance 2, so this is 1 over m3 scaling, one overestimate the data very clearly in the low mass region, while this other model, which has the two components model of the photon and the rho, has this freedom when one can fix these two components. And we show the two cases, one when the two components are added with maximum constructive interference. So this is this line, and the incoherently, this is this line. So this model with VDM1 seems to better describe the data with assumption that the interferences are maximally constructive. So one see this even better, showing this kind of effective transition form factor. Here you see this excess as a function of invariant mass, as a function of this is compared to VDM1 and to VDM2. So this is what I have said before. So one see this enhancement here, nicely described by VDM1. And there are also other models which we are now used in a comparison. So this is ongoing. There are more and more models coming in. So one is the models of the Ramalho and Peña. This is this form factor model, which I was introducing to you before. And this is shown by this red line. Actually goes also quite well through the data. And the other model is based on the Lagrangian effective model developed by the group Darmstadt-Budapest group. It's based on vector dominance 1, and this is really a prediction, was not tuned to data, it was calculated, and just compared to this what we have measured. And here the result is shown by this dashed green line for the phase phase between the coupling to photon and to pion of 90 degrees. So that also goes quite nicely I mean, at least in part through the data, but this model has to be still confronted with the bounds which exist from the PP and the photon approximation. So, I mean, and additional information which we got from our experiment, and it's really very interesting, it's based on the measurement of the polarization of the virtual photon. Here, this is decomposed, this amplitude is decomposed in the spin density matrix formally. So you have a free spin density matrix elements, which we were able to determine from the data, and they really give information about the production process, namely this free coefficient, this spin density matrix. Example to disentangle between the production source, which has based on the spin and the parity. So, for example, for the spin and the parity 1/2 plus or minus, one expect no dependence on the angle on the cosine theta of the virtual photon of the spin density matrix, while for the and the 0 for the ρ1 0. While for the higher spins, like a 3/2, one do expect some dependence on the theta and also not vanishing ρ1 0. That indeed is a prediction of this effective Lagrangian model, which indeed shows that in agreement with this, what we have learned from partial wave analysis, that this is really dominated by N-star 1520.
You have 1 minute left.
Yes, and I want to give you some outlook. So the outlook is that we are going to continue with experiment with the ion beam. So there will be, I mean, we hope that we will get the additional beam time, and we want to address the measurement at the third resonance region to conclude on the baryon transition form factors in the third resonance region, particularly for the resonances around 1700. We expect the much improved precision in this experiment. And we do also want to address the same measurement, the issue of vector meson effects, cold matter effects on vector meson, which was also discussed in the Joachim talk. So you've seen this data from PP, which shows very strong, sizable effect of cold matter. In the PA reaction, we should benefit a lot from the much better sensitivity to the decays inside the medium. Namely, you see that for the kinetic energy 1.17 GeV in, for example, pion niobium reaction, the amount of inside decays of the rho and omega meson is really significant, and it's almost 100% for rho and 70% for omega. So one has much better sensitivity to the decays in signed medium at low momentum, where largest effects are expected. So here you see the projections on the statistic which we expect. And last but not least, the experiment which should start already next year is a PP run at 4.5 GeV. So here, I mean, the highlight of this experiment is to detect the Dulles decay of hyperons, which perhaps at lower energy are not very significant source of a E plus or a contribution to the raw meson in medium, but at higher energy, these hyperons also do play a role. And here, what we want, I mean, they have a sizable decay branches in the photon, and that is expected to be measured in this experiment in the Dulles decay, which involves the lambda and the virtual photon converting to E plus and minus. So here you see the projections of this experiment, which allows, which we do hope that will allow us to separate the contributions from the hyperon Dulles decay thanks to the width, the narrow width of the hyperons. So this is much easier experimentally from this point of view to extract the Dulles decays from the hyperons. So that's my summary, which maybe I'm already behind my time schedule. So you can read it also, but what I want to stress that these measurements really do confirm that vector mesons do play really an important role in baryon virtual photon couplings. And this measurement with GSI pion beam are really especially beautiful examples how this can be precisely measured and how this hadron meson, raw meson couplings could be measured, and the benchmarking ratio could be determined, which is absolutely mandatory, I think, for after this these values were removed from the PDG. Yeah, so for 2022 and 23, I already told you what is our campaigns, and maybe I will close here and wait for your questions. Thank you.
Questions? Can you go back again for these comparisons between VDM1 and VDM2? I got kind of confused. What is now VDM1 and what is VDM2?
Right.
You defined this earlier somewhere.
Yeah.
So VDM2 is a Sakurai model. Yeah.
Right.
And the conclusion is that the VDM1 of Kroll-Lisomino works better.
Yes, I mean, yes. So this is actually this plot which this plot which yes, this what you said is exactly on this plot. So VDM2, which is that one which assumes scaling with 1 over m to the 3, and the saturation of a coupling through the raw meson is this red line, while the VDM1, which is this two-component model with the photon and the raw meson, I mean, one has the flexibility to tune the phase distribution, and bits. If one tune it in a way that it comes closer to the data, that corresponds in our simplified picture to the situation when, our simplified, because this is really experimentally based approach, not a theoretical calculations in a sense, but this seems to go very well through the data points, and that is also in a sense confirmed by this microscopic model based on this Lagrangian approach by Budapest GSI group, which is shown here. You see, this is really very striking and kind of for us, inspiring that this microscopic model, which is really has much more contributions as compared to the simple phenomenology which we did, seems to also confirm our conclusion.
Yeah, hi, Piotr, Ralph here. I'm also a bit confused about VDM versus VDM1 and 2 because, so I guess, yeah, go back to the figure. Yeah, so here you say the 1 over M3 versus M, but then on the figure, if you go to the figure, next slide, yeah, this slide. So the VDM1 actually falls off much faster, right? So
VDM1, yes, VDM1.
No. From zero, starting from zero, the VDM1 falls off much faster than the VDM2, right? But this is not what the 1 over M3 versus M would tell you, right?
Yeah, but you're right. But you remember in VDM1, remember there are two contributions. There is a photon contribution. So one adds two contributions. So one adds the contribution from a raw, which really falls down, as you see the function of M. So this is a raw contribution. In VDM1, the raw contribution is like that, as compared to the raw distribution from VDM2, which is 1/m3, and that is really very different. But in this model, one has also the direct photon coupling, which is here in principle given by our QED. So one has to make a sum of that one, and one has still a phase between these two contributions in our simplified experimentalist picture, and that gives you the total sum.
Okay, and what determines the normalization of the two curves at m equals 0? Exactly.
So that is this point here. So that the normalization is given by this cross section, which is measured in the reaction pi minus prot. Here is the reverse reaction gamma n going to pi minus proton. But one has to use the detailed balance, and one has the data point. So at 1.5 GeV, you have a data point which gives you the cross section for the n gamma. So that is really a well-defined number. And if you have this cross section for n gamma and one has a decomposition to the individual partial wave, one can construct this invariant mass distribution, knowing the spin and parity of the decay and having this QED prescription. So this is really, there are three bounds: the pion, the two pion cross section, the photon cross section, and then dielectron spectrum.
So in a nutshell, it's the photon point, the photon coupling, which determines that, as it should. Yeah. Okay. Thank you.
Yes. Exactly.
There is a question from outside.
Yeah, I just wanted to add. He had pointed this out very nicely with his data, but I think it's premature to conclude that VDM1 is better than VDM2, because VDM1, of course, has parameters in it which were fitted to the data here. The two components which he showed, the pure gamma and the one that goes through the row, they have to be mixed with some given phase, and that has been fitted here. Whereas the other one, it doesn't have a fit parameter in it. And if you induce another fit parameter into the VDM2, then you also get a good agreement on that.
Yes, no, absolutely true. But in case of VDM2, this 1/3, actually one has no any free parameter. That's what I can say, because you have this two pion spectrum.
Well, not really. The free parameter is somewhere else, namely in the VDM2, you have the row coupling to this transition from n star to n, and at that point there is a hadronic form factor, which has all sorts of free parameters in it, not only one.
Well, I don't know. Okay, I think we had a discussion on that.
We have to discuss that again, Piotr.
Yes. Right. We have already discussed discussion. But since I think the important point is that the base for the VDM2, the starting point is, let's say, this two pion invariant mass distribution, which one has in principle only to multiply by this ratio of these two decay widths. So the hadronic, whatever form factor comes between the resonance and the raw, in both cases is cancelled. So what stays here is the mass dependence of these two decay widths only.
Yeah, in principle that is true. However, the denominator, the rho to pi plus pi minus, only above 280 MeV. And you are interested in the region below. So this is really very nice. We have the very first data at these very low masses, but I think the interpretation is still tricky.
Yes, I agree with you. I hope that it will inspire some of your additions to do some thoughts about this, because for us it's a kind of surprising results and inspiring, I would say.
Okay, so thanks a lot. I think we can close for today. So thanks again to Piotr and also to all of the other speakers. So for today we are done.